Good morning, everybody. How is everyone doing on this Wednesday morning? So as always, just keep asking questions in the chat and sending questions by email, especially as we barrel down to the end of the quarter. So kind of crazy that we're already on week 9, although for us, we're basically ending week 9. All right, so let's start off with where we left off. So Monday, we just started introducing solutions. What are solutions? Kind of the components. Our thing being dissolved, right, was our solute, and then we're dissolving it in our solvent. And for our purposes, generally, water. That's just the nature of Gen Chem, right? A lot of aqueous solutions, so a lot of salts dissolved in aqueous solutions. And so now we need to get into the details. So the math, right? How do we actually make these solutions? How do we quantify them? How do we express those quantities so that, other scientists can understand what we mean? How can we communicate and share this information? And then, of course, do the stoichiometry. So this was our kind of quick overview. So I would recommend printing this page out or, marking it somehow electronically, because this is our quick shortcut. And we'll go through all of these in more detail. You can just kind of take a look at where we're going. So we'll start off with molarity. So this is kind of I would say the most common unit used, at least in chemistry. And so we'll look at this. So this is moles per liter, but again, we'll dive into it. And then not to be confused with molality. And so they're just different by one letter. And then what's kind of confusing, right, is just a little m. So molality. And that's moles per kilogram of solvent. Then we'll look at mole fraction. So that's amount of moles over total moles, which is related to mole percent. And then we'll look at kind of these parts by mass or volume. And then parts per million, parts per billion. So we'll go over those. All right, so let's look at this, right? So how do we prepare a solution from a solid? We have to know how much solution we need in total. And so for our in-person labs, we have a wonderful stock room, right, that has to run these calculations. And usually they start from a stock solution, so concentration of 12 molar, and then that might get diluted down to a 6 molar or 3 molar stock, and then that could be even further diluted. And so let's see what they want us to prepare. So it says we need to prepare 500 milliliters of a 5 gram per 100 ml solution. And so the important thing is to pay attention to the units always, because you never know what they're going to give you your concentration units in. So they actually gave it to us in grams per milliliter. So we have a gram per volume. And again, these units can vary. So they could have done grams per liter, but they didn't. So it's grams per milliliter. And then we can use our conversion factor. And so this one is easy, but there's different ways to say this. And so for water, right? So this is important because this is only for water. So water has a density of 1 gram per milliliter. So you can go back and forth pretty easily. And so another way to say this would be a 5% weight per weight solution. And so that would be 5 grams per 100 grams of water. And 100 grams of water is still 100 milliliters of water. So note, right, if you had a solvent, though, with a different density, you would have to convert, right, from milliliters of water to grams of water, or again, whatever solvent. And so for this one, we could even just do proportion, right? Make things simple. So we have 5 grams per 100 milliliter. And so we want 500 milliliters. So solving for X. Let me pull up my calculator. So then cross multiply to solve. 5 times 500 divided by 100. And so then we would know that we need 25 grams to go with our 500 milliliters. And so let's look at how we prepare that physically. And so now let's look at this little bit different scenario. So now we're saying let's make a 1 molar sodium chloride solution. And so then we would start by weighing out a mole. So, right, you figure out what a mole of sodium chloride weighs. So that's 58.44 grams. And so notice the physical steps. So first, right, you pour that solid in there, and then you'd want to, if there were still like little crumbs in here of sodium chloride, or again, whatever solute, whatever thing you're trying to dissolve, you could spray. In this case, right, we're dissolving it in water. So you would use whatever solvent. So again, in this case, water, maybe try to squirt a little water in there and, wash it down with a funnel. And then you start adding water. And again, you'd be rinsing down the sides and everything because you don't want to have, right, crystals stuck to the top there. And so you rinse it all down, fill it out about, 75% or so, 70%, just like around there. Make sure it's all dissolved. So you kind of mix it, you shake it. These things are called volumetric flasks. And so what's kind of cool about them is they're only made for measuring one measurement. So in this case, right, they use a 1 liter volumetric, since we're trying to make 1 liter of a 1 molar solution. And so once everything's dissolved and all mixed, then you continue filling it up all the way to the line there. And you can't go over, or else you have to start all over again, because then it'd be inaccurate. So then you get it right to the line. And then again, you might mix it a little bit more so you don't have, all the water sitting on top. So just kind of mix that, shake it up, and then you have your solution. All right. So solution, we have molarity. So molarity, we said, was moles per liter. So, right, molarity equals moles over liters. And this might be something that you want to put on a cheat sheet of yours. And so again, it's just telling us how many moles per solution, which we can convert to molecules if we needed with Avogadro's number. And so if a sugar solution concentration is 2 molar, right, we're saying it has 2 moles of sugar for every 1 liter. Or 2 liters has 4 moles of sugar. Or half a liter has 1 mole of sugar. And you can see how you could use your proportion to do that, or this kind of little formula here. And so you could plug in, right, 1 divided by 0.5 gives us back 2, or setting up your proportion, right? If we have 2 molar, we're saying we have 2 moles per 1 liter is equal to, right, 0.5 liters over 1 mole. And we could have set up a proportion, and you can do the cross multiplication to double check that. So 2 times 0.5 is 1, and 1 times 1 is 1. So that all, again, just checks out. And then molality, we mentioned, is defined as moles per kilogram. And so sometimes this is used in situations where you might want a greater accuracy. And so this is kind of the key. So it says that molality does not vary with temperature, since it's based on masses and not volumes. And, so the volume, does fluctuate a little bit with temperature, again, probably negligibly, But if you're trying to be really, really precise, you might want to pick molality. It's also, if you think how to relate this to cooking, right? People say that it's better to cook by mass rather than volume because of like packing differences. Just think of like a cup of flour, right? You could really smash that flour in there and really pack in a cup, right? Or if it's just loose, or maybe you sift it so it's even looser. And so, to be more accurate, and again, a lot of chefs say this or bakers say this, is you want to go by mass. And so we have our formula for molality. So moles of our solute over our kilograms of solvent. And so notice it's kilograms of our solvent, right? Not the whole thing. So this next one can be a little tricky. And the only thing I mean by this is we have to watch the units. So these kind of parts per parts, they could be given in a lot of variety of units. So that's what we want to take in here, right? It could be, pounds per gallon, kilograms per liter, grams per milliliter. So you just have to watch those units. And then, again, you can set up an appropriate conversion factor or proportion. And if you have any questions, again, always just reach out, send an email with a screenshot, whatever you need. And we also see this percentage a lot. And the easiest way to think about a percentage is it's in 100 parts. So if we have a 0.9% by mass, right, then that's 0.9 grams in every 100 grams to give us back, right, our percent. So if we have, right, a 9% by mass, then that would be, right, 9 grams per 100 grams. And so let's look at parts per million. And so parts per million can be thought of, right? Of course, this is a million. So 1 times 10 to the 6. So it's 1 per 1 million. So how many in versus a million particles? So that would be like saying, and so this is a good time, right? So you want to check out your local water. And then you can always look up your water report. And so usually with the water reports, they tell you the amount of toxins in like parts per million or parts per billion. So it depends on the toxin. And then, of course, what is allowed or appropriate. Sorry, trying to pull up the water report. Let me download it. All right, so while I download it, let's look at this. And so this works well. So it's thinking about, right, how many parts. So this would be grams of solute per 1 million grams, right? Or like you could even do 1 atom per 1 times 10 to the 6 atoms. But a better way and kind of easier way to think about it would be milligram per kilogram. And so this gives us our 10 to the 6 difference, right? Milligram is 10 to the negative 3 times our base unit. Kilograms is 10 to the third. So there's our 10 to the 6 difference. So that would mean, right, you find out how many milligrams of your solute you have versus your kilograms. So that would give you your part per million. All right, here's our water quality, at least for Medford here. And so let's look around here. And so notice the unit. So a lot of these are in the parts per million range. Yeah, so you can, you're going to have a lot of ions in solution anyways. And so it's nice as it tells you the standards. Let's start with fluoride. And so this one, right, this is not detected in the water. And then the standard level is 4 parts per million. And then we'll look at another one. So lead. So lead was not detected at this, again, parts per million. And so this is pretty good. And it is allowed to 0.015. Let's see what else. And then if you look at these bromates, so these are a lot lower for their detection. So parts per billion. And here are organics. So you would not want these in your water. And pretty good water report for this region. So benzene, and this is parts per million detection level. All right, kind of cool to take that in. All right, back to the units. And so let's go look at parts per billion now. And so parts per billion, again, we can think of 1 part over a billion parts, but I think it's easier to think of it in this way. So similarly, we could go, how many micrograms of solute do we have per kilogram of solution? And then that is equal to our 1 times 10 to the 9th factor, right? Microgram is -6. Kilogram is 10 to the 3rd. So there's our 10 to the 9th. Questions about that? And notice I kind of skipped over this. So this is milligrams per, right, a million grams. And there's your 10 to the 9th, right? So this is 10 to the -3rd. That gives you your 10 to the 9th, but this isn't as intuitive for me. So I really like this thinking about parts per billion like that. Questions? And so now let's look at mole fraction. So mole fraction is now parts over our whole component. And so there's our mole fraction. And we could, of course, have more things. So this is just with 2 things in solution, but we could also have, moles. We could do moles of C, right, over our total moles. So that would be moles A plus moles B plus C. We can do mole fraction with a variety of mixtures. And so this means, right, our total moles is equal to 1, and our mole fraction is always going to be less than 1, right, because it's a part of a whole. And then our mole fraction itself will have no units. And then we can also convert this mole fraction to a percent, right, by just multiplying by 1,000 or 100. And so you might see this used pretty interchangeably, right, the mole fraction versus the percent mole fraction. So another commonly used math is this one. So this is basically, okay, well, how do we take our stock solution and dilute it, right? How much do we know to make? So earlier we had looked at, right, how much solid. So this was kind of more of a focus on our solid reagent. How do we turn our solid to a liquid? And so again, right, that's what we just went over. But what if you already have a stock solution? Or sometimes what our wonderful stockroom does is, let's say they have a crystal that we want in aqueous solution. So maybe they make a stock, 6 molar iron chloride solution. But then for the lab, we only need 1 molar or 0.1 molar. So how do they know how much to dilute? And so the answer to that is this formula. And so this is the most broad version of the formula. So this is one that I encourage you to, have in your mind. And what's nice about this is so our concentration units can be in anything. And right, we just went over a bunch of units, and you'll probably mainly end up using molarity, but it doesn't matter because whatever your concentration is in this unit, that's the same concentration you'll get in those same units. You just want to be consistent. So that's the key. So just the same. So molarity, molality, right? Percent by mass. Just be consistent. It doesn't matter. Same thing with volume with this, right? Volume can also be in anything. So this is kind of nice, right? We don't have to convert between milliliters or liters. It doesn't matter. Just whatever unit you're in, be consistent. So just the same. Right? So again, either milliliters, liters, gallons, right? Just be consistent. And then sometimes you'll see in textbooks or internet sources, wherever you go, they tend to give it in this more what I call specific form, where our big M just stands for molarity here. So again, that's our moles over liters, but it doesn't have to be molarity. This is just specific to molarity, and it's given like this since chemists often use molarity. But I just don't want you to think, oh, I need a new formula if it's given in something else, right? Or you don't need to convert. Just make it easy, right? Just stay consistent with your units. So here's an example of what we might do or what the stockroom does for us. And so you have to kind of answer this question first. So let's just say, okay, I know for our lab, we're using a 0.5 molar solution of calcium chloride. And we need 3 liters of it, right, for our 2 lab sections. And let's just say they have a 10 molar stock solution. So the first question we have to answer, right, is how much stock? And anytime you see these dilutions, you're going to be thinking, okay, my C1V1 equals C2V2. So I'll just write that out. Now we can just start plugging in variables. It doesn't really matter who you call who, again, just as long as you're consistent. So I'll say this is our V2 and our C2, and we're starting with our C1, so I need to know how much volume. And so I'll plug in our variables, and I'll write my units so we know, yes, we're consistent, and what our answer is going to be spat out in. So we're solving for X is equal to 3 times 0.5. So now we can solve. Sorry, need more like screens or something. Okay, 3 times 5 or 0.5 divided by 10. So this is in liters, right? So we said X is 0.15 liters. So that's how much stock solution. So of our 10 molar stock. And so now that's what is going to happen. And so notice we have to have a 3 liter volumetric so we can accurately make 3 liters. So it has to be what our final volume is. And then we measure out 150 liters as accurately as we can. So our graduated cylinder is okay. If we were trying to go maybe more precise, we might want to use like a dropping burette or other volumetric pipettes. So then we get this in here. Then you start diluting it. So then we fill it up, maybe shake it around a little bit, and then continue filling all the way to our line. So again, you can't go over, or else you have to start over because it would be, again, inaccurate. All right, try this one for a second. You can always post your answer in the chat. So to what volume should you dilute 0.2 liters of a 15 molar sodium hydroxide solution to get a 3 molar sodium hydroxide solution? So let's see how you did. Again, you can still post your answers. So I would start off with just C1 V1 equals C2 V2. And so I'll just say, okay, here's our V1, here's our C1, and then, right, we want a 3 molar concentration. So what does our final volume have to be, right? That's what we're asking. Now just plug in our variables. And then we should get 1 for our volume. So did everybody get that? And so that means that we're going to take, right, 0.2 liters, so 200 milliliters, put that in to our volumetric. And you can tell I'm not an artist. So we said X was 1. So then this is our 1 liter volumetric. And then, right, we would take those 200 milliliters, pour it in here, and then dilute it to 1 liter. All right, let's look at a few other related properties. And so let's add to this kind of what this falls under. So this is called a colligative property, which basically just means solution related. So this implies, right, we have some sort of mixture of two things, so not a pure compound. So then, right, something's going to happen. And so let's look at what happens. And so we have this phenomenon called freezing point depression, and y'all are probably familiar with this. Although, so I assume most of you are based somewhere in Oregon. And so you notice in Oregon, they don't tend to salt the roads. They tend to put sand instead, or red rock. But kind of the point of that is to put particles in solution. And so what those little particles in solution do is they disrupt that crystal lattice structure from being formed in making ice. And so that disruption means that then the temperature would have to be lower to freeze, right? So now we have things disrupting our freezing pattern. So to get it to freeze, we have to go lower and lower that energy. And so that's where we get this expression, freezing point depression. So again, the freezing point of our solvent, again, usually thinking water or ice, is lowered. And so we also have this little graph here, which is nice. I can't remember if we've seen one before in this class. I feel like we haven't. So let's kind of walk through this. So this is just a temperature versus pressure graph that is showing us what states of matter it is in. Admittedly, this is not labeled as a specific solvent. So let's just say it's water. And our pure solvent line is along here. Again, it's not really labeled, just kind of broad, because we're just trying to see the effects of the freezing point depression here. But we're saying under these conditions, right, our substance is a solid. Under these conditions, our substance is a gas. Under these conditions, our substance is a liquid. And then we have, special states. So at this triple point, all three could exist. So at a pretty specific, right, temperature and pressure. But now let's focus in on what we care about. So freezing point depression. So that's going to correspond to this line right here. So this line corresponds to melting freezing. And we can see that because it's the boundary of our solid and liquid. So as it crosses over from these pressure conditions, right, so slightly changing or raising the temperature, then we go from a solid to a liquid. And then the key point is, well, then this line is moved lower. So now it has to go to a lower temperature for a solution. And then this is another situation where those units are really going to guide us. So let's look at our unit. And so we have this thing called our freezing point depression proportionality constant. And so on an exam, you'd have to be given this freezing point depression constant. And so it's saying that whatever solvent you're at, so let's look at a table so we can have some context. So let's say for water, so now let's focus on water. So it's KF, so that, again, this is for freezing melting. So it's 1.86 degrees Celsius per molality. So note that, right? All these ones are molality. And we said, right, that was moles per kilogram. And so this means for every molal of solute that's dissolved, then our temperature is influenced by 1.86 degrees. And since it's freezing point depression, it would mean, right, a 1 molal solution would lower our temperature of water, and it gives us a normal freezing point. So starting at 0 and then minus that, so that would be a negative 1.86 degrees Celsius for a 1 molal solution. And so again, watch those units. So we end up with our change in temperature is equal to, again, molality times our Kf. And so that molality will cancel with your units of Kf to give you degrees Celsius. And so this is, again, the text that kind of goes along with what I was saying. And so let's just think about salt disrupting our equilibrium. So again, it disrupts that packing. And so these salt particles also kind of dissolve in water, but they do not attach easily to ice. And so what you find that kind of freezing does is it helps purify the water and kind of gets rid of some of those ions right from that freezing of the crystal lattice. But again, we have to lower our temperature to go back to equilibrium. And again, here's our chart with just a few solvents. So probably mainly focusing on water. And on an exam, I would likely give you the constant. So you're not trying to hunt around or looking at textbook. So I would give you KF and KB if you needed those. All right, try this one. And this one's could be a little tricky, but just read this closely. So it says, what is the freezing point of a 1.7 mole aqueous ethylene glycol solution? So if you're live in the chat and I'm moving too fast, you can always yell at me to slow down. If you watch this later, of course, you can always pause me. And so let's look at the key point, and I highlighted it. And so, it's 1.7 molality of ethylene glycol in aqueous. So this is water we're talking about. And so we're trying to figure out the deviation from our normal freezing point of water. And then this means that we have our Kf here. So that's 1.86. And then again, we have our units. So degrees Celsius per molality. And so now we can plug it into our formula. And again, we don't even need to really look at our formula. We just have our Kf factor, or given our molality. And so we're going to see, okay, well, I'm going to get temperature out. So our change in temperature is going to be 1.86 times 1.7. Let me pull out my calculator. And so I get about 3.16, or I guess I should round it to 3.2 with our sig figs. And so that means, a change in temperature. And so luckily, water has a 0 freezing point, so we can easily do the math. So then our temperature freezing of our solution is negative 3.2 degrees Celsius. Questions on that? And so just like we had freezing point depression, now we have boiling point elevation. And let's go back to this graph here and look at what we're focusing on. So now we're looking at this line, these lines over here. Let me pull up color. Go with the crazy one. And so now we have our evaporation line. So evaporation, condensation. And again, we can see that from our liquid to gas here. So we were at a liquid, now we're at a gas. So let's focus on our pure solvent first. So we said pure solvent in blue. And then so notice how the solution raises the temperature. So we have our temperature going in our x direction. And so in a solution, we have to go to a higher temperature. And so we scroll back down to our text. So yes, we get the expression boiling point elevation. And so that is saying, so the boiling point of a solution is higher than the boiling point of a pure solvent. And so this is for a non-volatile solute, aka right, a solid. It's too big. Solid. And where this would not apply is, let's say you mix like two solvents together, like if you add ethanol in water, right? That is probably going to, if anything, lower the boiling point because that's a volatile solvent. So that there's the distinction. And so again, it depends on this new constant. So now we have Kb instead of Kf, so makes sense. And so again, boiling point elevation. So you're just figuring out now how much higher your solution boiling point is than the pure solvent. And one, just like before, it depends on our units. In this case, we're given in degrees Celsius per molality. All right. So let's try this practice problem. So what mass of ethylene glycol in grams must you add to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius? Oh, and you might want the Kb, so let me give that to you. So our Kb for water is 0.512. So Kb H2O 0.512. All right, let's check in. So this one is a little different, right? So let's break down kind of what it's asking. What do we have? Well, we're given that we wanted a change in temperature. So now we're saying, okay, my change in boiling point temperature is going to be 5. And we said that that is equal to the Kb times our, molality. So then we have our formula here. So now let's start plugging a few things in. So we have our Kb. So now we need to solve for molality of solution. So let's do that. Solve for molality of our ethylene glycol. So now I'm just plugging in. So 5 equals 0.512 times molality. So now I get a molality. Oh, let me read that one more time. 9. And let me keep in mind, so we have 2 sig figs. So 9.8 molal solution of ethylene glycol. Now the problem is it asks for mass. And so now this is tricky, right? So what is molality? So molality was moles over kilograms. All right, so we said, well, we have 1 kilogram of water. All right, so now we can start setting this up. So 9.8 molality equals, well, we have 1 kilogram. So that means we're going to need 9.8 moles of ethylene glycol. And now from here, it's just a moles to mass conversion. And with that, we need the molecular weight of ethylene glycol. And let's add it up for fun, right? So they gave us the formula. So let's go ahead and add that. So 12.01 times 2 plus 1.008, times 6 for hydrogens, plus, I'm going to round to 16, times 2 for oxygen. So about 62.068. And let's just go ahead and multiply that. And so we need 608 grams. Any questions about this one? All right, after we finish this, I think we should do a molarity stoichiometry problem. And so let's just finish up with the last of these colligative properties. And so osmosis is just defined as the flow of solvent from a solution of low concentration to a solution of high concentration. And so if we zoom in on this depiction here, so we start off with our initial conditions. So notice on our left side, we have solute particles. And then on our right, we only have water. And then if we let that go, we see that the water level rises. And so that's from, right, our water trying to achieve equilibrium. So it attempts to dilute this. And then however much it rises is equivalent to its pressure. So this gives you the osmotic pressure. And if we could apply pressure to this, so we would keep this flow from happening. So that would be, again, the osmotic pressure. And so it's given by this formula here. So we have our osmotic pressure, and this is big pi, is equal to molarity times our R. So this is our gas constant, times our temperature in Kelvin. But actually the better formula should be written like this, IMRT, where I is this thing called the Van Hoff factor. But all it's really telling us is, well, how many particles in solution does something make? And let's dive into this. And so for our purposes, we're going to go by the expected Van Hoff factor. And so let's start with the first scenario. So we might have a non-electrolyte. So again, think of any molecule, aka sugar we were discussing, right? So we said, well, sugar doesn't light up the light bulb. And so that would give us just a factor of I. And so all this is saying is a 1 molar sugar solution is still, right, 1 molar of things in solution. Now let's compare that to sodium chloride. So sodium chloride, right, so we have 1 molar solution of sodium chloride, except it dissociates into 2 ions, right, sodium and chloride. So even though you have a 1 molar solution, you have effectively, right, 2 molar of ions in solution. And so let's keep going. And if you note, like magnesium sulfate here, it's a little bit larger. So apparently its true measured Van Hoff factor isn't quite 2. But again, for our purposes, it disassociates into magnesium and sulfate. So it has a Van Hoff factor of 2. Let's look at magnesium chloride. So if we have a 1 molar solution of magnesium chloride, it will disassociate into magnesium and then 2 equivalents of chloride. So that's 3 molar of ions in solution. And then looking at iron chloride, so we could do 1 molar solution of iron 3 chloride. And again, that would go to 1 mole of iron and 3 equivalents of chloride. So 4 molar solution effectively. All right, questions about that? And let's look at a few definitions. And so if we look, we have an isoosmotic solution here, or isotonic. And all that means is that the solution has the same osmotic pressure as the solution inside the cell. So even though, right, there could be water flowing in and out, there's no net flow of water. So however much water is leaving is also coming in. If we have a hyperosmotic or hypertonic solution, then our solution has a higher osmotic pressure, aka, right, there's more ions in solution. And so that means all the water flows out of the cells, right, trying to get the system back in equilibrium. And that would cause our little cell to shrivel. And so you can think about that, right? You don't want to have a diet too high in sodium. So all that could cause, right, the water to rush out of the cell, not good. Could also lead to high blood pressure because of that. More, fluids in your veins, fluid retention. And then the last one is hypotonic. So that means our solution has a lower osmotic pressure than the inside. And so that means there's water flowing into the cell, causing it to swell. And so this is why things like, those gallon challenges where you try to chug a gallon of water, that could be bad. Because, right, if you drink too much water, that could lower your ions too much. And then this can happen, right? And, your cell could even burst, which, is how bad things happen with those challenges. And, some people die from drinking too much water, which is crazy. So I'm looking for some stoichiometry questions with solutions. All right, I guess this one works. So let's try this one out. So we're looking at this reaction. So we have magnesium hydroxide plus hydrobromic acid gives us magnesium bromide and H2O. And let's try this one. So it says, how many milliliters of 0.225 molar HBr would be needed to completely react with 3.26 grams of magnesium hydroxide? So try this out for a second, and then we'll go over it. All right, let's start walking through this together. And so let's walk through it, right? So this is a stoichiometry problem, except we just have a little extra step. And then instead of grams or moles like we've been used to, now we have molarity. And maybe even write what molarity is. So that's just moles per liter, right? Not a big deal. And it's asking for milliliters. Okay. And let's just double check. Balanced equation. Good. Okay, 1 magnesium, 2 bromines. Let's see, 2 oxygens, 4 hydrogens. Okay, balanced equation. And then to do our stoichiometry, right, we have to get in moles. We have to compare moles. So we can tell they're in a 1 to 2 mole ratio. And so let's start. So we have 3.26 grams of magnesium hydroxide. And this time I'm going to look up the molecular weight of magnesium hydroxide. And so I see that it is 58.32 grams per mole. So then we divide, right? So 58.32 grams. Moles goes on top. So now this is moles of magnesium hydroxide. But now we need moles of HBr, right? So let's do that. So for every 1 mole of magnesium hydroxide, we need 2 of hydrobromic. And I'm going to stop there for a second just so we can kind of check in. Sorry, trying to put my calculator somewhere where my head isn't in the way. So dividing, right, how much we were given, our amount, divided by molecular weight. So that's moles of magnesium hydroxide. Multiply that times 2. And so I'm going to write this number down. So this is saying how many moles of HBr we need. So we need 0.112 moles of hydrobromic acid. And so now we can set up our molarity, right? So now we have moles per liter. So now we're starting to get there. So now we're saying, well, we have a 0.225 molar solution. I need 0.112 moles of this. So how many liters do I need? And we're going to divide, but let's look at this dimensional analysis so we are all on the same page. So if we divide by our molarity, so that's moles over liter. So moles cancels to give us liters. I also like the triangle trick. So again, molarity equals moles over liters. We can rewrite as our triangle. So moles, molarity, liters. So if we're solving for volume, we cover what we're solving for. So cover up L, and it tells us what to do. And so if we cover up L, well, that's interesting. I don't see the eraser. But then we see we're left with moles over molarity. So let's plug this in. And remember, we're going to get liters, but it's asking for milliliters. So we're going to have to convert. All right, so we're given 0.497 liters, which would be 497 milliliters there. Oh, I think I wrote something wrong. Oh, no, I didn't. It's fine. Okay. Any questions about that one? All right, this is a good one to practice. Again, you want to be comfortable with the stoichiometry solution scenarios. And so just keep asking for help if you need it. I know it's getting to the end of the quarter, but it's been really great. I do miss seeing your faces. I'm always sad teaching online because I really like the student interactions. That's what teaching is about. So again, if you want to say hi, you can always meet with me in person on the Medford campus. I'm more than happy to do that. All right. Again, email me if you have any issues. I want to hear from you. Otherwise, have a great rest of your day and a good rest of your quarter as we start to wind down in our last almost 2 weeks now. So yeah, it's been fun. All right. Have a great day.